So here they just wanted the, basically the y equals mx plus b for the line that they described. The first one had a slope of 3 and a y-intercept of 0. So your function looks like this, f of x equals 3x. The second one had a slope of 1 and a y-intercept of 5, which they actually handed you the y-intercept right there with your 0, 5. But it's f of x equals x plus 5. So we're used to x squared. You can get any number up there. And so your graph actually changes depending on what's going on. And we're going to do just a little bit of it today. As we go along, we're actually going to see what causes it to go through a graph, what causes it to bounce off a graph, depending on what power you're talking to. You also can look at the powers and determine what happens at the end of the graph. And so looking at your function and your exponents in your function will actually help you get a picture of what's going on with your function. Just like your discontinuities help you get a visual picture of what's going on with your function. Your powers do as well. All right, something like this. Where is it? And they're describing. And so the first thing we are going to talk about is end behavior. The first one that they give us an example are two functions that we've seen before, x squared and x cubed. All right, x squared and x cubed. X squared we know is a parabola. X cubed, hopefully you remember, looks like this little curved line that keeps going. All right. And these are both continuous functions. So we have different examples of power functions, and they give them up here. We have, I'm going to pull this down some. We have y equals negative 3x squared, x to the 1/3, y equals 1 over 5, x to the 4th are all power functions. And then these are exponential. This is what I was describing earlier, and I said it backwards. So 2 to the x is actually considered an exponential function. Y equals 6 is actually a linear function, all right? And so for it to be considered power, you actually have to have your power in there. We also are going to get to some direct variation, which look like similar to these. These are our variation functions that we're used to. But this, however, is a linear function with variation. These two would be power functions with variations, okay? And so when you start seeing exponents, then you start getting a picture of what's happening. Left end and right end behavior, all right? And they literally mean, when you're looking at the graph, the left side of the graph and the right side of the graph. What is the graph doing as it goes to the left? What is the graph doing as it goes to the right, all right? And they describe it with this limit notation as x approaches negative infinity. So think of your coordinate plane. Negative infinity for x is that way. Positive infinity for x is this way. Left side of the graph, negative infinity. Right side of the graph, positive infinity. Okay? And so they describe it with this limit notation, but they're really just saying, well, negative infinity, what happens as you look to the left of the graph? Positive, what happens as you look to the right of the graph? All right? Now, they've used these two examples, x squared, and you'll notice that with this guy, if I have the left side of the graph, I'm going constantly to positive infinity. The right side of the graph, I'm going constantly to positive infinity, right? Look what happens with cubed. The left side of the graph, I'm going to negative infinity, but the right side of the graph, I'm going to positive infinity. This one is very intuitive, okay? First of all, it's always talking about like you would read it from left to right, okay? So you're always, as if you would read it from left to right, what's the graph doing, okay? So as we're reading it from left to right, the graph is increasing. That is visually obvious, right? As we read it from left to right, the graph is decreasing, obviously decreasing, right? And then you have this piece of it. They're only talking about from here to here. This is constant. Obviously, it's not changing, okay? So while we're talking about walking along the x-axis from left to right, when they talk about increasing, decreasing, they're talking about what is y doing. Because if you're going from left to right for x, x is always increasing, right? That's how it works for left to right for x. So when they talk about increasing or decreasing, they're technically asking what is y doing as you go from left to right, okay? So they've written it like this. The function is increasing if over L, or this little piece right here, f of x2 is bigger than f of x1. That means as you go along, you're getting bigger, increasing. F of x2 is less than x1. As you're going along, decreasing. F of x2 equals x1. You're not changing constant, okay? So increasing, decreasing visually is very easy to see. You can definitely see what's going on with the graph just by looking at it. You may have to walk it and say, okay, from here to here, we're decreasing, then we stay constant, then from here to here, we're increasing, okay? So you may be given intervals as to what's happening. As you can see from this guy, your intervals could change, but visually it's easy to see what's happening with the graph. The next definition they're gonna throw out here are the terms even and odd, okay? Even means that you could replace every single negative x every x in the function with a negative x and it would not change the function. Odd means if you put a negative x in for every single x, it's going to negate the entire function, okay? So I'll give you an example. If I have y equals x squared, if I plug in -1, it won't change that. Like if I plug in a negative x, why? Well, plug in a negative x for x squared. What does that equal? X squared. It didn't change my function. Right? Does everybody see that? But look what happens when I change that to y equals x cubed. Let's plug in a negative x for x and make it cubed. What happens? Well, I end up with negative x cubed, don't I? It negated my entire function. This one would be even. This one would be odd. Okay? This one would be even, this would be odd. Right? So we should be able to talk about domain. Why? Well, we should be at this point able to say whether or not there are any problems in the domain. So for the first one, are there any problems in the domain? There are not any problems in the domain. So the domain for this one is going to be all real numbers. Or you could say negative infinity to positive infinity. If you want to do it in set notation. Many ways to tell me what the domain is, okay? Domain. We're not going to talk about range right now. End behavior, okay? So we are going to talk a little bit about end behavior. This is to the 5th power, all right? And if you start looking at the patterns, to the 5th power is going to go opposite direction. It's actually going to do exactly what my cubic function did. Now, it's going to look different because of that 1/5 in front of it and because it's going to have some loops in the middle. But it's an odd number of exponents. It's actually going to look exactly like my cubic one. So for this one, to the left-hand side, it's going to go down. And to the right-hand side, it's going to go up, just like my cubic function did. It's going to do the same thing. And again, it's going to do stuff in the middle that the cubic function did not do, but it's going to follow the same pattern. All right? So if it follows that same pattern, on the ends, we at least know if it's increasing and decreasing. Let's talk about even, odd, or neither. All right? Even, odd, or neither. So even and odd, 1/4. What happens when I plug in a negative x and take it to the 5th power? What's going to happen there? It's going to negate the entire, I could just write it like that. So what is this? Even or odd or neither? Odd. All right? So for right now, we're only going to worry about end behavior and odd. All right? And even then, they didn't give us a bunch of information on even and odd. We'll get to that when we do the rest of them. I just want to introduce it a little bit today. So for -2x to the 4th, if I plug in a negative x and take it to the 4th power, what's going to happen? It's going to be what? Positive x times -2. Did this guy change at all? It did not. So what is this? This one is even. All right? Even and odd. So when you have something to a negative power, they're actually moving towards 0 because you have to think of the opposite of like what's going on with an asymptote. It's actually flipping and putting x to the bottom. And so anytime you have 1/x, which is basically what this function creates, x to the -1, those are actually moving towards 0. Both of those are. And so on the left and right-hand side, you're moving towards 0 because you actually have an asymptote at 0. Think about this. The function looks like this. Non-removable problem at 0, right? And so both of these are actually moving towards 0. It's not going to be an infinite limit there. All right, so when we do direct variation, you're gonna have to remember these guys here. Y equals k to the x, and that's just gonna be replaced with squared, cubed, whatever it is. And we're gonna do inversely too, but for the homework, it's just gonna be these. So you don't have to worry about 18 or 20, just do number 30. I just want you to do one variation, and then we'll do some more of your end behavior when we get to the shortcuts and when we get to our graphing calculators.